We acknowledge the first Australians as the traditional custodians of the continent, whose culture is the oldest living culture in human history. We pay our respects to elders, past, present and emerging, and we respect their cultural heritage, beliefs and relationship with the land. We extend our respect to all Aboriginal and Torres Strait Islander people here today. They share the memories, traditions and hopes of the traditional ancestors with the new generations today and in the future. We would also like to thank them for looking after this land for thousands of years.
Good afternoon, everyone, and welcome to day 4 of SciFest 2023. Very excited to have Ben from Physics Education joining us today to talk about embedding science into your lessons. So this is things that you can do at home, you can do in the classroom, and just have a lot of fun with some really simple ideas. So I'll hand over to Ben. Thank you once again for joining us, and I look forward to seeing all your ideas.
Thanks so much, Karen, and glad to have everyone here. I know that we're going to be very busy doing some science stuff, and don't worry if you got no materials. In fact, I never expect you to have the materials. You can always look at this later on to your heart's content because this is recorded. And hi to those people who are watching the recording now. Yes, my name's Ben. I'm from a place called Physics Education. We don't spell so well. This is us, physics, but we teach science in this padded room all over the world in lots of different ways. So what are we doing today? We're going to spend some time looking at some simple materials that you can use to talk about variable testing, which is really the heart of how science really works. It's really the scientific method. And you don't need fancy materials anyway. You can totally get it from the local shops and it will not cost you that much money. In fact, I would put money on that you would have some of these materials at home. So let you know, for those people who are actually here, welcome. I'm glad to have you here. And actually, by the way, I'm hanging out in Western Sydney and Darugland, and definitely want to acknowledge all elders past, present and emerging in my area as well as around the country. Okay, so look down the bottom of your screen. There's a Q&A function. I will keep an eye out on that in case you've got questions to ask or stories to tell about any of these particular experiments, because this is unlike a student session. We're all adults here, which means whilst I've presented some of these myself, there's a good chance some of you have done the same. So I don't want to just be me just chatting at you. If you want to share ideas or comment or question here and there, please be my guest and share, and I'll put that out to the group as well. Okay, so there is no rhyme or reason in this. We're going to do heat, we're going to do forces, we're going to do sound, we're going to do chemistry, and hopefully you walk away with a bunch of ideas that you can do. So let's stop rambling. Let's start doing. Let's do some science and some variable testing. So I am going to change my view to a completely different camera over here. Now, the reason why is we're going to use some blocks that, whilst I bought these from a particular science supply store, you could emulate this same experiment. Now, I've got a little bit of rubber here to hold back the eventual melted ice that we're going to melt on these two tiles. Now, the thing about these two tiles is they are different. Before we go into what makes them different, let's look about what makes them the same. Getting kids to understand what variables are and how we control variables is really fundamental to how science works. The experimental question will be, if we put a block of ice here and a block of ice here, which one will melt the ice first? Now, I have aluminium and I have plastic. Both blocks are the same size, they're the same color, they're the same volume, they're in the same airspace. Everything about them is the same, except one is aluminium and one is plastic. Now, you guys can't feel it, you're somewhere else in this country, but I can. When I feel the plastic, this one, it feels sort of room temperature. When I feel the aluminium, it feels cold. So my question to you is, out to the group, and I can see your questions as they come in on Q&A, which one do you believe, and it's okay if you get it wrong, but which one do you think will melt the ice first? On the aluminium or the plastic? I'm going to keep an eye out and see what you guys think. I'll give us like a couple of seconds to type it. And if I get no typing, I will just do the thing. But it's always nice to know what you think. So have a bit of a guess, knowing that the aluminium feels cold and the plastic feels warm. All right, looks like no one's typing for now. So let's do the experiment. Now, if we're doing this, we should talk to our kids what makes it fair. I'm going to put my ice blocks on at the same time. Ready? 1, 2, 3, go. And if you look at it, look what's happening to, yeah, look, we got so once someone's gone for plastic melting faster. Thank you for going for that. Well done for asking, answering. But the answer is, and I need my O-ring to hold it back, the aluminium that feels colder, the ice is melting faster on it. No, it genuinely feels colder. I'm not making it up. The plastic feels warmer. And yet, not much is happening to the ice cube here at all. Now, you could really get into the detail about how fair is this experiment. Maybe should I have the exact number of milliliters of water that made each amount of ice? They need to be the same size. Perhaps it's unfair if they're not in the exact same spot. I mean, if you're doing a true science experiment, you should keep everything the same and only change one thing. So, we've seen, assuming that we've controlled our variables reasonably well, and I think we've gotten pretty close, you've seen that the answer is rather clear. The aluminium melts the ice faster, which means we're sort of on our way towards reporting what's going on. We've got our results. The question is, what do you think makes this happen? What do you reckon? What's your guess? In Cyberland, those people who can type away in this live session, what do you think's going on? You can see it's totally, this is almost dry. Like a little bit of water's on it, but not the same as this total mess. It's just everywhere. Why is this the case? I mean, if I get the same ice cube and put it on the plastic over here, it doesn't do that much. And then if I put it back over to the aluminium here, it starts melting again. Why is this the case? It's okay if you don't know, but throw your ideas out. I mean, part of science is throwing your ideas out and testing them. All right, so your answer is, if I take our ice cube away, there we go, take it away. And rather than just, oh, well, maybe we'll look at it for a moment. This feels cold because it takes heat off my fingers and drags it into the aluminium. Aluminium is a really good conductor of heat, whereas plastic is not that great at all, or at least compared to aluminium. So why does it melt that ice cube? It draws heat from the table up through the aluminium and into the ice cube. Whereas the plastic doesn't do that well. It's really only allowing for that ambient temperature that's sort of sitting around it, and it doesn't really melt all that fast. So what we're seeing is a counterintuitive experiment. You expect that the thing that feels cold, this one, wouldn't melt the ice much. But that really makes you sort of question what we think heat conduction is. This material absolutely is transferring heat up into the ice cube. Is showing that the thermal conductivity of aluminium is much greater than the plastic. So it's really good as you look at what you might be able to do with your students is think about what experiments can I do that will throw them, that might make them guess something. And then if you do something that goes against their expectations, they're more likely to remember what happened. So I'm going to quickly just take this off looking at those blocks for a moment. And I'm going to bring it up to my face again. And let's chat about what you could do where you are. Now, I bought those blocks from a group called Educational Innovations. I bought them about 15 years ago, something like that. I've been using them for years, but you don't need them. You know how you can get those, you get your metal baking trays and you can get those silicon ones? Well, they're two different surfaces, right? If you put, and even like you use cupcake trays so they can kind of contain what you're doing, contain the mess. You could have some silicon cupcake trays, some metal cupcake trays, put them on your table and go 1, 2, 3 ice cubes in, and the silicon doesn't transfer that much heat and it doesn't melt your ice so much. And the kids can literally feel the two different trays, and they'll feel that the metal tray feels colder, which means heat is leaving their hands faster because the metal is more conductive to heat. So it's counterintuitive and it works. So the point of that experiment was to look at how hyper, and I'll hold them up to us, how hyper controlled this experiment is. They are the same size, volume, color, everything about these materials are identical. The only thing that you're changed are the two materials, which means it's a very fair test. The only thing that you could probably do that would be unfair would be to have different sizes of ice, maybe put them in different locations, or maybe some of the ice has a different material added to it, like cordial or orange juice or something. All right, so let's move on. We've got a heap to do. Now, remember, in the Q&A, please ask questions or comment throughout. That way we can sort of make sure I'm covering what you want to do. Now, teachers, you will remember as you went through your university course, you will have gone through Psychology 101. I mean, it's a very standard thing, educational psychology. And you might remember Piaget's pendulum. Now, Piaget's pendulum, if you think back to the time and going out to do this experiment, it was all about looking at concrete learning, concrete thinking, formal thinking, where is your student sitting at? So what we're going to do is apply this experiment from a scientific basis, and we can talk about the psychology as well at the same point in time. So there's a few different ways you can set up a pendulum, but honestly, all you need is a stick. I'm using one of those retort stands that you would screw into a base in a chemistry lab, but I just grabbed it and I've got a stick. Now what you need is a string, because you're making a pendulum, and you just get your string, and you wrap it around just a couple of times around your pole so that you can pull it up or it can come down. So you've got something that you can swing with, yeah? Okay, you're going to need a mass at the end of your pendulum. So in this case, I'm using modeling clay, and I've got 2 bits of it. So for now, I'm going to use half of it. I'm going to use the yellow one. I'm going to make it into a ball, and I'm going to put it round the end of one of my strings. My question to the group, sorry, you're going to get lots of questions. I can't help it. But my question to all of you, what affects the speed of the swing of the pendulum? I wonder if you remember. Is it the length of the string? Is it the amount of mass, so the heavy bob at the end of the string? Is it like, if it's heavier, does it swing faster? Or is it both? Or perhaps, is it nothing? Nothing affects its speed. Nothing affects what's called its period of swing. Do you know the answer? So in Cyberland, if you want to throw your answer out there, feel free. It's always nice to know what you think. But I've just got my bob here all set up now. I've just wrapped it around my string. It's a brutal way to do it. You could tie washers on it if you'd like, but modeling clay is frankly faster. All right, so what do you think? I'm keeping an eye out on the Q&A, and if you're watching the recording instead, have you guessed before I do the experiment, yeah? Because that's how science works. We have a guess, a hypothesis, a educated guess. All right, so doesn't look like anyone's going for the answer. All right, so we're going to do the experiment. I'm not going to change the mass at the bottom. Now, if I was doing this really fairly, I'd have this fixed somewhere so it's not like wobbling around. I'm going to try and keep it fixed. If I was going to try and do a bit more fixed, I can probably use this bucket that I've got here for another experiment later. So I'm just going to hold it there and make sure it's not dangling on the desk. There we go. Not on my, there we go. There we go. So it's not touching anything but the air. So we've got that there swinging, and I've got the label there so you can kind of see its difference. Now I'm going to let it go at the same height each time. That would be fair, right? So I'm going to watch this, and you're going to watch this. I'm going to count slowly. If we were being even more scientific, we'd use a stopwatch. But let's see how fast it is with this length string. Okay, you saw that speed. What if we add more mass? Now I'm going to make sure that I don't make it much longer. I just dropped on me. Oh dear, so I'm just going to squish it on there now, which means I have messed up my experiment. That's okay. I've got extra weight on it now. I've put the orange one on top of it as well. How about we vary we put this on and let's see if it makes much of a difference. Oh, I'm gonna make sure it's at the right height. Oh, it's hitting my table. That's the problem when you're trying to do it with only one set of hands. Okay, this is much easier than group work. All right, here we go. Go out. Go further out. There we go. My hands are in the way. There we go. All right, letting go. So it seems to be about that speed. What if we make it shorter? I know you're like watching me fumble away on the TV here, but then you can kind of have a wry smile as I struggle with it. This bucket is actually messing me up more than anything else. All right, we're gonna go again. We're getting that speed. Now let's make it shorter by pulling it up. Faster. Now we'll put it down again. Slow. Now pull it up. Fast. Let it drop. Slow. Pull it up. Fast. It's much faster when you shorten the string. Now, with a controlled experiment, you'd be able to make sure and see if I'm right. But this is a variation of Galileo's very old experiment, his observation when he was sitting in a church watching a chandelier swing on the roof. And he queried, I wonder if it's the weight, the mass of the chandelier swinging on the string, or is it the length of the string? And a lot of kids will think that it's the weight that matters. You could try doing the same different weights on the same length of string. I promise you it goes the same speed. It's just a bit hard with my fumbly hands. It really does. It goes the same speed. It's not the mass. Now you might be wondering, well, why should this matter? In fact, you might be wondering, why does the ice cube thing matter? Well, thermal conductivity with the ice cube is important for materials and heat conductivity. In terms of pendulums, it can even affect things like amusement park rides. Years ago, I remember going to, and I won't name this space, the spot, so it'd be unfair to the provider, but you know those giant swings where you put yourself in a sling and they winch you up and they let you go? On their advertising at the ticket booth, they said, if you go with a friend, you'll go faster, which is completely incorrect. Now, what they're really doing was increasing their money per hour by having more people go through it, right, per hour. But I don't know if they knew this or not, but my suspicion is because they're ride operators that need to know the physics of what's going on so they don't hurt anyone. They were well aware that adding a person on the end of the same length of string would not make a single difference as to how fast they travel through the air. Certainly more fun flying through the air with your friend on the swing like that, but it absolutely did not affect the speed of the swing. The only thing that would have made a difference is not having a huge swing that they've got in the first place. It would have been actually making it shorter. It would have gone faster, but that would have made a shorter ride, nowhere near as thrill-seeking. So in a way, it's an example, a straight up example of science not meeting reality, or at least the amusement park ride not meeting reality of how things work. All right, so that's one. It's also known as Piaget's pendulum. Keep an eye out for your students who might mesh the variables. Make them a table, or get them to make a table. Long string, short string, heavy weight, light weight. There is a matrix of 4 different tests they've got to do. Short string, heavy, short string, light. Long string, heavy, long string, light. Keep an eye out for students who only do 2 tests. Quite often you'll have a student that will only do short string, lightweight, long string, heavyweight. They'll only do 2 tests, which gives you an idea of the way they're thinking. That's what Piaget was talking about from their psychology point. But from a scientific standpoint, we've got to be able to isolate our variables and test each one accordingly. Yes, I was a bit messing up with my hands, but that's the point, was that sometimes theory meets practice can be sometimes a bit hard, especially if you don't have enough hands to do it. But there you go. So that's the pendulum one. Now we're going to show you another physics-based experiment, which also can go counterintuitive to your class. We're going to investigate gravity in this room, and it's going to use some really simple stuff. In this case, it's going to use a piece of paper and a book. That's it. And they're both the same size. Yes, it says there are 100 free experiments. In fact, there is a link that Virtual Excursions Australia will send out. There are over 250 free experiments on their website. I'll make sure they will get that out to you soon enough. It's not just blatant advertising. It was just an A5 size paper that I knew would fit my A5 size book. Let's do an experiment on gravity. So what we're going to do is we're going to go further out because I need to. I'm going to walk around and let's drop this. If we drop our piece of paper and a book at the same time, which one will hit the floor first? In fact, because you can't see the floor, I might stay out here for a little bit. We'll go this way. Which one will hit the desk first? If I hold this up like this at the same height and I'll let it go, which one will hit the desk first? In fact, think about what would the students write? What would they say if we had a book and a piece of paper and you let it go at the same time? What do you think will hit the ground first, the table first? They're probably going to guess the book, right? So we'll try this. 1, 2, 3, going. Yes, the book drops down and it hits it first. Why? Why is this the case that the book hits the table first? Well, the temptation is to say that the book is heavier. And that's true. The book is 100% heavier. It has more force through the air because the stuff literally has more mass. And when you have mass and it's moving, it's going to have more force than something that's lighter. That's true. But is it really that heavy things fall faster than light things? It's a really big temptation is to stop the experiment and just believe that heavy things fall faster than light things. Now I'm going to walk around and grab that piece of paper that fell. Let's see if we can do another version of the same experiment and isolate what's going on. So if I put my piece of paper under the book and I let it go, 1, 2, 3, yeah, they fall together. And you'd ask the kids, why is that the case? Well, the kids will say, and I understand this, that the heavy thing's pushing down on the paper, it's going to stay together. I get that, fair enough. So what if we put the piece of paper on top of the book and repeat the experiment? Let's see what happens now. They went together. In fact, if you quiz your kids, quite often they will say the book will separate and drop first and this will flutter down. And yet, when we do this again, you'll see it absolutely does not. They stay together. So, I might just sit down here for a moment. And apologies to what I'm doing to the microphone. The microphone's not far from here, so I know it's making a bang in your ears or as you watch this. Why does this fall together when the paper is on top? What's your best guess? Now, it's okay if you don't know. I'm just curious to see what you think. I want to make sure. In fact, you can even repeat this in your room as you're watching me, because I wouldn't be surprised if you got a piece of paper and a book somewhere. Just make sure you're dropping a book that you don't want to break. But why? Why does it do this? Now, I'll let you know that I haven't finished the experiment yet, though. But this is just a little thing. All right, so we're going for gravity. Fair enough. In what way do you mean gravity? Is your thing the gravity affects the book more than the paper? Or is it something else? Well, the answer is about air. The way we're going to do this is investigate the air itself. If I go further out again, so I get a chance to drop it higher. Remember when I put it next to each other, like that, the book totally beat it to the table, right? Had more force. Now, that's a well-constructed variable in terms they're the same sizes of paper. Same A5 size, right? But what if I get the piece of paper and scrunch it up? Now, I haven't made it heavier or lighter. I've just reduced its size as it passes through the air. So we'll try this again. We've got my book, we've got my piece of paper, and we're going to drop it at the count of 3. 1, 2, 3, dropping, and they hit at the same time. And yet if I open it up again, just to labor the point, I open it up again. Now it flutters. Why? What is going on that is making this happen? Why is this the case? What do you reckon? What's your thoughts? Now, I know it's like it's the afternoon, it's middle of science week. I don't want to think right now. I just want to see what you think. All right, so the answer, it is about air resistance. So when I scrumpled up the piece of paper, it reduces the amount of air it's got to pass through, which means it has less friction, it has less air resistance. So even though it hasn't got much force, whereas the book does, they fall at the same speed. You could look up, and I'm not going to share the video, you can go look this up another time. Look up Apollo, hammer, feather, moon. Apollo, hammer, feather, moon. You'll find it on YouTube and whatnot, and you'll find a video of one of the Apollo astronauts physically on the moon dropping a hammer and a feather on the moon in a lack of atmosphere on the moon, and they fall at the same speed. Now, the same experiment got repeated again by Professor Brian Cox from the UK, and in this case he had a bowling ball, I believe, and a feather, and was dropping it in a vacuum chamber, and we saw that they fall at the same speed. On Earth, gravity affects everything the same amount. The acceleration due to gravity is, if you want to be more sciencey, it's 9.8 meters per second per second. That's the acceleration. It speeds up 9.8 meters per second every second. Per second per second, that's what that means. It speeds up the same rate, and it doesn't matter what object you're dealing with. The only thing that matters is how much air resistance you got. Now, a really useful analogy to talk about with your students about this is, think of someone skydiving. If they're skydiving and they jump out of the plane and their parachute opens, they're happy, catches the air. If they jump out of the plane and the parachute does not open, they are not happy. They're going to fall faster. Their mass never changed. The weight of the parachute, the mass of the parachute is the same whether it's open or closed. Just when it's open, it catches more air, right? It has more air resistance. So you make a profound difference to the speed that you fall, the acceleration that you experience, if you can get some air resistance to happen. That reduced it massively. So there we go. So we've just done 3 experiments where you can isolate variables, which uses really simple stuff. Now, how about we show you just a little bit more? I'm going to do a little bit on sound. And I mean, I could ramble all day. I mean, there's thousands of experiments we have to know. But for now, let's do a really simple one on sound. Now, I'm going to do one which involves a straw. And I do know that these straws, you're not going to find them so much anymore. I know that we've gotten rid of plastic straws because they're an issue for the environment, being a single-use plastic. We've got like 10,000 of them left over, so we're going to keep using them to show this. You can use bamboo straws. It works the same way. We're going to show you how sound changes due to the length of an instrument, and we'll discuss why. So for now, what we do is we flatten the straw. That's what we do. We flatten it out, and we get our scissors, and we cut it one way and the other way, and now we've got a point that will vibrate. So it's kind of like I've cut it into an arrow shape. Now, if I blow through one end, not much happens. If I blow through the other end, it vibrates. Now, at this point, we're going to change it, and we're going to see what will happen. My question to you is, if I shorten the straw, will the sound get higher, lower, louder, softer, or not change at all? What are your thoughts? So listen to it again while you type it in. All right, so we've got some guesses for higher. Let's find out. So I'll do it one more time, and then I'll chop, yeah? Yeah, higher. In fact, if I chop it again, even higher. And I'll do it again. Even higher. So the question is, why is this doing this? So I'll do a quick drawing for why it's doing it. So I'll go over this way, over to my whiteboard, and I'm going to use my thing here. Now I'm going to make a, like we've got bits here that we may get to, we may not. I've put out way more than we have time for, but we've got here my straw, And inside my straw, when I was blowing it, was a sound wave. Now, sound waves have that shape. Now, when you shorten an instrument, now I'm just thinking it's slightly blurry, so I'm going to give it a bit of a, there we go. Sometimes it just loses its focus. All right. Okay, so sound waves can be short or long. So when I shorten the straw, 1, 2, 1, 2, we squished up the sound wave. Just by shortening the straw, we just see a massive difference in the sound. It became a higher pitch. What we're doing is we're changing the frequency of that of the wave. Frequency literally means how many times does it go up, down, and back again. That's called a hertz. Hertz is a measurement of frequency, up, down, and back again. And the faster, the more times you can go up, down, and back again in a set amount of time, the higher the hertz, the higher the frequency, the higher the pitch. And when you shorten an instrument, you shorten the wavelength, the frequency, and so it gets higher in sound. All right, so that's a very, very easy one you can do. Let's look at the speed of vibrations and see if that makes a difference as well. So if we go over this way, I'm going to go close down to my hands this time. So we'll go over here. I have a balloon, and with our balloon, I'm going to get a metal nut. Now, as I do this experiment, have a think about other things that you could do to change this experiment to do other variable testing in the version I'm going to do now. But all we do is you put our metal nut inside our balloon. There we go. And we blow it up to about that size, so about a bit bigger than your fist, and then we tie it. That's all we got to do. All right, so at this point, we just want to hold it like that. And as we move it around, it'll start to swirl around the balloon, and the corners of the nut vibrate the balloon, and you get, well, this sound. Here we go. And you can hear it. Now, if we speed up that movement, will that sound get higher or lower? What do you reckon? That's the question. What do you think? Will it get higher or lower if we do this? Let's find out. So hold it, get it going, and then I'm going to speed it up. It goes higher. It definitely goes higher. We'll do it slow. In fact, what we'll do is we'll get it really fast, and then I'll stop, and then it'll keep on whirring around and slow down. Listen to the sound change. Here we go. We'll get it going. There you go. So the faster you go, the higher the vibration, faster the vibration, the higher the sound. You will have noticed this with anything. Anything that's vibrating quickly makes a high sound, whereas if it's vibrating slowly, it makes a low sound. And it's something you can really easily do. In fact, if you're looking about variable testing, it really is quite irrelevant which material you're going to use for your science investigation. As long as you only change one thing and then see the effect, you're doing real science. Now, a lot of kids will expect that you're meant to get a result all the time. Like something should change because you did a science experiment. But science experiments sometimes have no change. If nothing changes because of whatever you did, you changed a variable. If nothing changes with your results, that is still a result. It just means that changing that variable makes no difference to your experiment. That's still a result. In fact, I know of students that have wanted to throw out their experiment because nothing changed. I'm like going, well, you've already got an answer for one of your experiments. In this control, this test, this sample, when I varied this one thing, it had no effect. That is still a valid thing to report. I mean, I suppose the next job is to go, well, what if we change another variable? Let's see what happens then. I mean, that's really the scientific method in action. It's working your way through the process until you see something that affects your experiment. Your job when you're doing any of your science experiments in your classroom is just to make sure that you're not confounding your experiment. Confounding the experiment is when you are changing more than one thing. And so when you get a result, you've got no idea if making the experiment hot or making the experiment longer, or whatever it is that you did, you don't know which one made the difference. So I very much, when I teach our students about variable testing, we talk about this is the time to be a control freak. If you're all about control and you want to make stuff work perfectly, like really clearly, perhaps you might be a really good scientist, because a really good scientist will want to control everything and just change one thing. In fact, they get really splitting hairs. They'll start splitting hairs on how much you can control something, because they want to make sure there's no other external factor that affects their experiment. It's actually quite important. All right, so let's do some more experiments that you can do. So how about, we haven't got too much time remaining, what if we show you a simple experiment where you've got to kick what might be going on? So I want you to have a look over here. I'm going to go over here. All right, so this is called a poly-density bottle. In the bottle is clear liquid and 2 sets of beads. If I move it, you can see they slosh around. So what we're going to do with our poly-density bottle is we're going to move it. If I turn it around, what do you think might happen? So let's do it. Around we go. And those people who have picked that the white one goes above, yeah, you're correct. The white one has less density than the blue beads. Now, the harder thing to pick is, why are they in the middle? We've got this clear liquid above and this clear liquid below. What's going on there? Well, even just throwing that out to your students, maybe they'd say, what if you shake it? Well, that's what we're going to do. You shake it up. So shake it up completely, and now this is where it gets weird. Put it down and look. The white ones go to the top of the bottle and the blue ones go down to the bottom of the bottle. But that's not all that happens. As we watch it, and it takes a little bit of time for it to happen, but it's already starting to do it now. As we watch it, you can start to see a change again. I can now see that the white beads are going downwards and the blue beads are going upwards. Now, if you're really observing, now let's be honest, a little bit hard to see from where you are. It's rather clear at the top, it's pretty clear underneath, it's a bit murky in the middle, which is telling you something. What do you think might be going on with the liquids and the beads? How is this working? That when I shook it up, the white ones went to the exact top and the blue ones went to the very bottom, and after waiting for a while, these beads come together. What do you think's going on? Just curious. This is a bit of a harder one. I thought I'd throw this one as a bit of a harder one to discuss at the end of this session. What's your best guess? Because this has now gone back to where we started again. And I will say we've been running this experiment for at least 15 years. Physics has been going for about 19 years, so we've got a lot of stuff hanging around. What do you reckon? What do you think's going on? The answer is, they're not just one liquid. 2 liquids. What we've got, and we didn't give you all the, all the background, and that's quite deliberate. What we have are 2 liquids. The bottom liquid is water mixed with salt. Water mixed with salt is dense. The thing at the top is absolutely not water. It's isopropyl alcohol. That's, that rubbing alcohol, also known in Australia as isocol, the one with the crocodile on the front. Rubbing alcohol does not mix very easily in water. And it just happens to be that these two beads are just the right densities that they sit at the boundary layer between isopropyl alcohol and water with salt in it. Now the white ones are very much lighter, but when you shake it, the two liquids mix, so the densities change because whilst the liquids all mix in such a way that the blue beads for a moment in time are the most densest object in the whole mixture. And the white beads were the least dense of the whole thing. But then the liquids start to separate again, and your isopropyl alcohol wiggles through the beads, goes to the top, and the salty water wiggles through the blue beads and goes down to the bottom, and it pushes these two together, and it's kind of a nice little experiment. So it's about not just observation, but trying to think through what might be going on. And it's okay if you don't know what the materials are. You can kind of have a guess of what might be occurring, and then you do the reveal later. Bit of messing around to get it right, but you can make these. It just takes a bit of to and fro to do it. Now, we've only got a couple of minutes left. I do really want to share some free resources that are on our site, and there's several hundred of them. They really are. So I'm going to quickly share my screen. It will not take long. There are over 250 free experiments on the Physics Education website. If you look in the top left, that's how you spell physics, and you just click on where it says free resources here. It opens up to a whole bunch of stuff. There are podcasts, science trivia, over 300 teaching articles. There's a lot of stuff in there. But if you go in the free experiments area, it is what it says. There are hundreds and hundreds of, several hundred free experiments that you can totally use. Now you can see down the bottom, there's something we're doing during Science Week where we're actually doing some teaching units. There are teaching units we've built out that you can use even if you don't get us to come out to your school. So if I clicked on that and I use this yes25 off code, there are complete teaching units on states of matter, forces, motion, light and color. There are heaps and heaps of them. The electricity, you get the idea. And there's even a science bundle, a whole bundle, which pulls this all together that you can use. There's several hundred PDFs, coloring in sheets, worksheets, all the different scope and sequences, all the things. If I go to the geology thing, you can see that if I go to the top, the course curriculum for the geology one, it is what it says. Printable experiments, cross-curricular teaching project ideas, it's all there. And it's something that we've developed out so that people can use this with their heart's content and on demand. And there's a lot of stuff in there. It's all curriculum linked and very, very, very handy to use. So we've only got a couple of minutes left. I thought I will stop sharing for a moment and just see in the time that we've got what time. Oh, what are the beads, please? The beads, you've got to go get, they're just beads we got from Spotlight. And you just got to get a few different types. It's been so long ago, I probably should have taken note of the brand. But that's just been a matter of, beads that you like that the kids will make little bracelets out of. You just got to trial different ones till it works, and off you go. All right, any other questions that have come up? So thank you very much for that question. No worries. Okay, so we've got a little bit of time. You might be curious as to why I have a bucket over there in the first place. It wasn't just sitting there randomly. I thought we might just finish off with one more experiment that you can use. So I'm going to do a film canister rocket. So I'm going to go down nice and close so you can see. Film canisters, I might go down a little bit because you can't see it so well. There we go. So our film canister, you can get some vinegar into your film canister. So I'm going to do that now. In we go. I'm just going to go a bit lower here so you can see what I'm doing because that's quite full. I could have a very, very short amount of vinegar in there. And in the base here, we're going to put a bit of bicarb soda. So when I get some bicarb soda onto a plate just behind us so you can see what I'm doing. So I'm going to get a small amount of bicarb soda. In we go like that. And I'm going to make it wet. So we'll get our water. There it is. And we'll pour it in. There we go. And now we get sticky. And we're going to see if this thing launches. So by having sticky bicarb soda paste, this won't come out of my lid. And at this point, whoa, just dropping it. We can, I'm going to put my glasses on, with my cups, stop it from hitting my roof. course it has a lot of power, we're going to see if we can change the variables by just having the size difference with the amount of vinegar that you use. Let's try quarter full, going now upside down, put this on, and we wait, and it builds up pressure and it pops. Now I put the cups on to stop it from going too high. Let's try it this time with full vinegar, and it'll be our last part of our experiment. So I put it all the way up to the top. Ooh, I need some room to be able to put the lid in. There we go. And I get my lid, get some fresh baking soda on top of it. Now it's full. Will it go higher? Let's find out. Now the last one popped up to the top of my bucket. Let's see if it goes all the way up for this one when it's full. Ready, set, upside down. Will it do it? Will it do it? Will it do it? Will it do it? Guess what? That's all you get. It doesn't do that much. It is too heavy. Turns out it is actually, truly is rocket science. If you have too much propellant in your rocket, you've got to lift the propellant too. If there's not enough force to do that, in that case there was not, it could not go up. So look, thank you so much for hanging out with us for SciFest. This is very much a part of National Science Week, and was brought to you from Virtual Excursions Australia. So I hope you enjoyed this session. It was very lovingly put together as a National Science Week project supported by the Australian Government, Inspiring Australia, which is an Australian Government initiative. Thank you so much. This is Ben from Physics Education, and thank you very much for Virtual Excursions Australia as well. I hope you enjoy the session. See you later, everyone. Take it easy. See ya. Bye.